All right, guys, if you will, in your notes, find the page called Definite Integrals. Excuse me, that's what we're going to talk about, okay? Sorry that I can't be here yet again, but you have Miss Bellinger, who's the greatest of all time. So here we go, okay? The area under a curve. We talked a little bit about area yesterday, and we learned how we can make rectangles, okay, to approximate area under a curve. And it turns out, and this is very, very cool, and we're going to talk about it on Friday on Fundamental Theorem of Calculus Day, that we can find the exact area under a curve, okay, by what's called a definite integral, which is this kind of sort of funny looking thing right here, okay? It looks like our integral, except now we have this number down here and this number up here. Okay, and if you look at the picture, that represents basically the number beginning on the x-axis to the number that we end on the x-axis where we want to bound our area. Okay, so our area is bound on the top by our function, the integrand, on the left by that bottom number, okay, the bottom of our integral symbol, and on the right by that top number. Okay, this definite integral gives us a number. It is an area. It is a numeric value. Remember, when we just had, what we talked about yesterday, when we just have this, which we called an integral, we're going to give this a more specific name now. We're going to call this an indefinite integral. Okay? So we have a definite integral and we have an indefinite integral. The only difference are the a and the b, okay? Whether you have numbers at the top and the bottom of your integral symbol or if you do not have numbers. The indefinite integral is an antiderivative, okay, with a plus c. So that means that this is a function. This indefinite integral is a function. Okay, it gives us, when we evaluate an indefinite integral, we get a function of x. When we evaluate a definite integral, we get a numeric value. Okay, that's really important to remember. Our calculator will, remember how it can find derivatives for us if we do Math 8? We can also solve definite integrals in our calculator, and we can use Math 9. So if you remember yesterday, we were trying to evaluate the integral from 1 to 4 on the square root of x dx. And I know we didn't quite finish those notes from yesterday, but we will. We'll go back and talk about it, okay? Fear not. So we were trying to evaluate this. There was no way we could make a geometry problem work for that region that was underneath this curve. But if we get out our handy-dandy calculator, and I'll show you, if we type in Math 9, oh goodness gracious, it's so exciting. Okay, it looks like an integral, right? If our bottom number is 1 and our top number is 4, and inside my integrand, I type a square root of x, and then that dx, which remember I told you, we're going to talk about it on Friday, the integral at the beginning, the dx, which is called a differential at the end. Why are those bookends, right? It's a big mystery. It's very, very exciting. Can't wait to tell you. And we get an answer. Our calculator told us an answer. And our calculator's even so smart that I believe it's going to give us a fraction. So we can get an exact answer, just like if that region, that shape, underneath square root x from 1 to 4 was like a geometry shape, right? A shape that we learned from geometry. Okay? So let's do a couple. Let's practice doing a couple of definite integrals. This integral from -1 to 1 of 2 minus the absolute value of x dx. Okay, what does this graph look like? Well, the minus sign is a flip. Okay, you got absolute value, which is a v, flipped over the x-axis, and then up 2. So it's going to be this graph right here, isn't it? Okay, and then this integral from -1 to 1, what does that mean? That means the area under the curve. So we're so glad Miss Bellinger's here because this does make a geometry formula, doesn't it? Or a shape from geometry. We have a rectangle and we have a triangle. Can we find the area of those two pieces? Kind of looks like a house. I believe we can. That rectangle has a base of 2 and a height of 1, so its area is 2. And then this triangle is 1/2. It also has a base of 2 and a height of 1. So we get 2 plus 1, which is 3. So I'm saying that this integral from -1 to 1 of 2 minus the absolute value of x is exactly 3, which is kind of cool. and kind of makes sense, right? We can see it on a graph. We can also type it into our calculator just to show you. Where did we go? From -1 to 1. So if we go from -1 up to +1, I hope you guys are doing this with me in your calculators, to minus, remember how we get absolute value, right? Math over to the number menu, and it's the first choice, dx. Be sure you type in that x, and be sure you're using the x that's up here. I don't know if you can see my blinky cursor. The button is red. Be sure you're using that x, okay? Oh my gosh, my calculator agrees. This is such an exciting day. Okay? Now, this next one, graph the integrand and use the area to evaluate the definite integral. Well, this one's a little bit trickier to figure out. I hope that you guys remember we did one kind of like this yesterday. To figure out what this integrand looks like, I've got a function, the square root of 64 minus x squared. And when we looked at this, or one very similar to this yesterday, we said, what if we would square both sides? Because square roots are weird, right, to look at. And then if we added the x squared over, then we said, oh yes, this shape is very, very recognizable. That's the equation for a circle, right, with a radius of 8. And we also said that because this up here is just the positive square root, it's really only the top half of the circle, correct? Correct. And we want the integral, which means area under the curve, from -8 all the way to +8. Those are x values, right? From x equals -8 to x equals +8. So that shape is a semicircle whose area is 1/2 the area of the entire circle. So we get 1/2 pi times 8 squared, which is 32 pi. Now here's what's very exciting. If we were to type this into our calculator is going to go ahead and put the pi in there, right? There's no way for me to recover that. I'm not going to be able to get an exact answer. But because you all are very, very smart, much smarter than your calculators, you recognize this as a geometry problem disguised as a calculus problem, right? And so you said, I can draw it. I remember from geometry what the area of a semicircle is. I can get the exact answer with the pi in it, which of course is much, much, much better than some crazy decimal with decimal points that go on forever and ever. Okay? Good? Good. All right, let's look at this one. Use geometry, not Riemann sums, to evaluate the following definite integral. Oh, I didn't erase my work, did I? I guess you guys have my work. So we've got this piecewise function, right? And so obviously this is the right graph. We've got the a function where when x is less than or equal to 4, we have this horizontal line y equals 6. And then when x is bigger than 4, we have this diagonal line 2x minus 2. So a slope of 2 and a y-intercept of -2. So if you look at the graph, obviously you can see this does give us geometric shapes that we can figure out. It looks like we've got a rectangle down here that is 6 units wide and 6 units tall. So its area is 36. And then we have a triangle on the top. Okay, so we got to figure out our triangle. Its area is 1/2 base times height. And its base is 2. You can count the blocks or figure out the intersection point. And its height is 4. And 1/2 times 2 times 4 is 4. And so the total integral, because I took my two geometric shapes and added up their areas, is 36 plus 4, which is 40. So far, so good? Yes, 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 yes. Okay. This is where things get a little bit tricky, right? You guys are all with me to here, yes? I hope that's true. Okay, if not, of course, we'll talk tomorrow. But this is where things get a little dicey, because right here, I have this region that extends below the x-axis. Okay, so the figure to the right shows the area of the region. So I have a green piece above that's got an area of 15, a green piece above that has an area of 13, and then I have that weird little tiny jaggedy looking piece, almost triangular, that has an area of 4, but it's below the x-axis. Okay, so because in calculus, we don't deal with scalars, we deal with vectors. Okay, something being below the x-axis, as we know, makes a big difference, right? That means something. Okay, and what that means is that the integral from a to b, of f of x dx is equal to -4. Okay, that piece right there has an area of 4, but because it's below the x-axis, okay, its integral is -4. So when they ask us to find the integral here from a to c of f of x dx, okay, you're not going to add up the areas of those two pieces. You're going to have to decide which pieces have a negative integral and which pieces have a positive integral. So from a to b, we get a value of -4. From b to c, we get a value of +13. Okay, and so our integral, which deals with signed, S-I-G-N-E-D areas, is equal to 9. Okay, we're going to talk about some properties of integrals later on in these notes that I hope makes that a little bit clearer. I hope that's not just total nonsense and confusion to you. But here we go. The figure to the right shows 4 regions. Okay, R1 and R2 and R3 and R4 all have positive areas, don't they? But the integral from, let's say, pi to 3 pi over 2 would be negative. And the integral from 3 pi over 2 to 2 pi would also be negative. Okay? This is a graph of x times sine of x. We want the integral from 0 to pi over 2, sine of x dx, which is easy peasy. It looks to me like it's just the area R1, which they tell us is equal to 1. Okay? Let me do one that's a little bit trickier that they didn't ask, but I'm going to ask. If I wanted to integrate from pi over 2 to 3 pi over 2, this same function, okay, which I can write, we know what it is, don't we? It's x sine of x. Then I would say, well, from pi over 2 to pi, it looks like I have the region R1, which is pi minus 1. Do you guys see that right here? And then from pi to 3 pi over 2, I have the region R3, but that region is below the x-axis, and that means something to us. So we have to subtract. So we're going to subtract this region right here, minus pi plus 1. Okay, so let's see what happens. That gives me pi minus 1 minus pi minus 1. Don't forget to distribute your minus sign. The pi's cancel, that's very handy dandy, and I get an integral value of -2, which tells us what? Really answer me. What does it tell us? Hannah? Julia? Emma? James? Nothing? No? Yes? Did you get it? Did you get it right? Did you? It means that we have more area below than above the x-axis, doesn't it? Right? If our net area, okay, or integral, right, comes out to be negative, then it means that basically R3 was bigger than R2, doesn't it? There's more area below than above the x-axis. Seems very geometry-ish, okay, and for now has no real meaning, but on Friday, Fundamental Theorem of Calculus Day, we're going to talk about why that is such a big deal, okay? I'm going to stop this video for now and give you guys a chance to rest or maybe write anything down, and then I will have another video for you for the rest of these notes.